Yeah, welcome. So we are discussing about artificial neural networks. Let us continue with our discussion. So in this lecture, we'll be discussing about various neural network architectures. So basically here we'll be discussing three architectures. These are single layer feed forward architecture, multi-layer feed forward architecture, and recurrent network architecture. So basically there are many different architectures of neural networks are available, but these three are the fundamental classes of neural network or artificial neural network architectures. Okay. So before getting into this architecture, let us first try to understand how neural networks works with a simple AND problem. So in the logic gates we have AND. So let us try to understand how neural network works for the logical AND. So this is the truth table for the logical AND operation with two inputs x1 and x2 and output y. So when the input is 0, 0, the output will be 0. 0, 1, the output will be 0. 1, 0, the output will be 0. 1, 1, the output will be 1. So the output will be 1 only when both the inputs are 1. Okay. Let us try to understand like how we can design a neural network for this scenario. So the neural network should take these inputs. What are the inputs? These are the possible inputs it can take 0, 0, 1, 0, 0, 1 or 1, 1. So at every point it has two inputs, and it should make some processing, and it should produce output as what, either 0 or 1, right? It should produce either 0 or 1 as the output. So it is something like binary classification. So this will be our representation of the neural network. It has two inputs. We'll call it as x1 and x2, and that is given to a particular unit which performs the weighted sum. X1 is connected with the weight W1, X2 is connected with the weight W2. So basically then here what is happening is X1 W1 plus X2 W2. So this value we compare with some threshold value. If this sum, if it is greater than some threshold value, then we produce the output as 1. Otherwise we produce the output as 0. So this is what here we are doing. Now this is a very, so this is the overall model. Now we should know for what value of, so here the 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 core crux in the neural network is identifying the weights. So how will we assign the weights? So for what weight, for what value of weight, this neural network will work properly for the AND logic. So here we are not discussing like how we arrived these weights. This is a very simple problem. So we can do some error and trial method, and we can decide the values for weight and threshold. So not only weight, we should also decide the value for the threshold. So this is a very simple problem. With some error and trial, we can identify these weights and threshold. So let us assume that this is the weight we are going for. W1 is 0.5, W2 is also 0.5, and threshold is 9.9. Okay. So this is a perfect value of W1 and W2 and threshold, which will properly work for the AND logic. So how it will work in the sense, so let us take the case of x1 and x2 being 1. Okay. So if x1 is 1 and x2 is also 1, then what happens in this case? 1 into 0.5 is what? 0.5. Again, so this is, so here what is happening? Here basically x1 w1 plus x2 w2 is happening. So it is 1 into 0.5 is 0.5. This is x2. So this is also 1 into 0.5 is 0.5. And then we have to add these two. So 0.5 plus 0.5 is 1. Is 1 is greater than 0.9? Yes. 1 is greater than 0.9, so the output will be 1. Right? But for all other cases, it will produce some value which is less than 0.9. So the output will be 0. So if you take the second case, like say x1 is 0, x2 is 1. So in this case, 1 into 0.5 is what? 1 into 0 into 0.5 is 0. 1 into 0.5 is 0.5. So 0 plus 0.5 is 0.5, which is not greater than 0.9, which is less than 0.9, so the output will be 0. Similarly for 1 0 also, right? For 0 0 also the same thing happens. When it is 0 0, both will be 0, right? So obviously 0 plus 0 0 0 is less than 0.9, so the output will be 0. So here we are fixing the values of W1 and W2 and the threshold, and we make sure that this neural network functions properly for the AND logic. Now this is an example of a single neuron. Actually, this is an example for a single neuron, but this example can be stretched for a single layer neuron. This example can be stretched for a single layer feed forward neural network. So a typical single layer feed forward neural network will look something like this. It will have some m inputs, x1, x2, x3, so on and so forth, up to xm inputs. And it will have some n neurons, and it has only one layer. So this is the only layer it has, and this layer contains n neurons. Neuron 1, neuron 2, neuron 3. All neurons are, each neuron is called as I1, I2, up I3 up to IN. All these are neurons. Okay. So if you take the first neuron receives input. First neuron takes input from all. I mean, the first neuron gets all the inputs, right? Or if you see the first input goes to all the neurons. It goes to first neuron, it goes to second neuron, it goes to third neuron, it goes to fourth neuron, so on and so forth. It goes to the nth neuron. Similarly, if you see the second input, it also goes to the first neuron, second neuron, third neuron, fourth neuron, so on and so forth, up to nth neuron. That is, every input is basically connected to every neuron. Such a network is called as fully connected network. Such a network is called as fully connected network. It is not necessary that it should be always fully connected, but if the input is connected to all the neurons, if all the inputs were connected to all the neurons, then such a network is called as a fully connected network. Or you can, more generalizedly, we can say that if the output of one layer is connected to the input of, if the output of one neuron is connected to the input of all the other neurons of the next layer, then such a network can be called as the fully connected network. Okay. So here what you are seeing, this is basically an example of single layer feed forward network, right? So why we are calling it as feed forward network? Because there is no feedback mechanism. So we are not talking about any feedback network now. There is no feedback. It's only feed forward. It goes only this direction. Okay. So there will be weights. So our in neural network, our objective itself is to learn the weights, because inputs, you have to predict the output. So now the output depends on what? Output depends on weight and the threshold, nothing else. So what we have to predict is, we have to predict the weight and the threshold, right? So typically, if you take a neural network, initially it will assign some random weights, right? It will assign some random weight, it will produce some output, and then it checks whether uh, the actual output that is produced, uh, it will be compared with the expected output. Okay. If and the difference will be taken, the difference will be treated as error, and based on that error, the weights will be adjusted. But that happens in a back propagation mode. That happens that is not a feed forward network, that is a feedback network. Okay. But we are not getting into feedback network as of now. We are starting with the simplest case, right? But I'm saying that you should understand like how these weights are getting adjusted, because that is the crux of neural networks, right? So here, if you see x1, if you see the first input, it is connected to all the neurons, right? It is connected to first neuron, second neuron, third neuron, so on and so forth, up to nth neuron. So it is connected to first neuron through the weight W11. So why 11? That because it's the first input connected to the first neuron, right? And it is connected with the second neuron with the weight W12. Why we are calling it as, this is just a representation, because the first input connected to the first input connected to the second neuron, so W12, and the weight associated with the third first input and the third neuron is W13, and the weight associated with the first input and the fourth neuron will be W14, and the weight associated with the first input and the fifth neuron will be W15, so on and so forth. So like that, we are assigning the weights. Now, similarly, you can also consider the weights for the second input. The weight associated with the second input and the first neuron is the weight associated with the second input and the first neuron is W21. Okay, this will be W21, right? The weight associated with the second neuron and the second input will be W22. The weight associated with the second input and the third neuron will be W23. So W21, 22, 23 up to W2n, right? So this weight basically it can be represented as a matrix. This weight can be represented as a matrix. So we can represent the weight matrix something like this. It is W11, right? W11, W. First, let us consider the weights of the first neuron. You take all the weights of the for the first input. So it is W11, W12, W13, so on and so forth up to W1n. Similarly, weights of the second input, W21, W22, W23, so on and so forth up to W2n. This continues. Similarly, the last input, WM1, WM2, WM3, so on and so forth up to WMN. Right? So the point is this weight can be represented something like a matrix. And right? Okay. So whatever we have discussed, that's what explained here. We see a layer of n neurons constitutes a single layer feed-forward neural network. Here we have n neurons, right? I1 to IN. So this constitutes a single layer feed-forward neural network. This is so called because it contains a single layer of artificial neurons. Why we are calling it as a single layer network? Because we have only one layer. There are networks with multiple layers. Now we are starting with the simplest case, which has only one layer. Okay. So this is what we have discussed. The weight can be represented to a weight matrix, right? Okay. Now the output of any kth neuron. So if you want, say the output of what will be the output of kth neuron. So if you see here, so this is I1, I2, I3, IK is somewhere here. So what will be the output of kth neuron? It is, so it is X, W. So what will be the weight associated with X1 with the kth neuron? Weight associated with X1 with the kth neuron will be W1K. With the second neuron will be W2K. I mean, the weight associated with the first input with the kth neuron will be W1K. With the second input and the kth neuron will be W2K. Third input and kth neuron W3K, so on and so forth. Mth input and kth neuron will be WMK, right? So the output produced at this layer will be what? It will be W1K plus W2, sorry. The input also you have to take. So it is weighted sum, right? So it is X in X1 into W1K plus X2 into W2K plus X3 into W3K plus X4 into W4K, so on and so forth. It goes on up to XM into WNK, right? So this is how the this is what the output will be, right? So to that we can also add the threshold or the bias. Okay. So actually if you see here the equation is given something like this. So the output OK is nothing but it's some function of W sigma I equal to 1 to M WIK into XI, right? So this equation is generalized, that's all. So it is up to it is going up to WNK, right? And it is going to XM. It is going up to from X1 to XM. It is going, right? so that here it is mentioned as sigma I equal to 1 to m wik into xi, right? So basically this m and n should be equal, so that here we are using the same term, right? Okay, fine. So so here we are, here from this network you can see there are, each input is connected to everyone. So basically we are considering is a fully connected network, so this m should be equal to n. Hence we are not using a separate variable here. So xi basically goes from what, 1 to m. As m is equal to n, this is fine, right? So to that you can also add this theta k. So normally we will subtract theta k, or this theta k you can also consider as a bias term. So normally we'll also include a bias uh, to adjust the parameters, right? Okay. So this is about single layer feed forward neural network. Right? Next, let us talk about multi-layer feed forward neural network. So the concept is almost same. In a single layer feed forward neural network, you have only one layer. But in a multi-layer feed forward neural network, you will have multiple layers. Okay. As a simple case, let us try to understand a three-layer model. Let us try to understand a three-layer neural network model where it has an input layer, a hidden layer, and an output layer. So this is the simplest example for a multi-layer feed-forward network. So we are going to discuss a multi-layer feed-forward network with I neurons in the input layer. The input layer contains I neurons. Okay, and uh, with, I input neurons, there is number of neurons at the first layer. Yeah, the input layer contains I neurons, right? And the hidden layer and the hidden layer contains P neurons, right? So let us see. Yeah. So it is sorry. The input layer contains I neurons, the hidden layer contains M neurons, and the output layer contains N neurons. So this is a example for a multi-layer feed-forward neural network with three layers. So this is the input layer. Input layer you can see it has I neurons. Hidden layer it has M neurons, right? And the output layer it has N neurons, right? Now let us assume the neural network has P inputs, x1 up to xp, right? And all these inputs where, for example, the first input goes to all the neurons of the input layer. It goes to first neuron, second neuron, third neuron, so on and so forth. Similarly, second input goes to all the neurons of the first layer. As usual, third input also goes to all the neurons of the first layer, so on and so forth. Now, the first layer produces some output, right? The first layer produces some output. Say the first neuron of the first layer produces some output. Again, that output will go to all the neurons of the hidden layer. The first output produced by the output produced by the first neuron of the input layer will go to all the neurons of the hidden layer. It will go to the first neuron of the hidden layer, second neuron of the hidden layer, third neuron of the hidden layer, so on and so forth, up to the mth neuron of the hidden layer. Similarly, the output of uh, the output from the second neuron of the input layer, the output from the second neuron of the input layer will also goes to all the neurons of the hidden layer. It goes to the first neuron, second neuron, third neuron, so on and so forth. So that is applicable to all the neurons of the input layer. The output from the ith neuron of the input layer also will go to all the neurons of the hidden layer. Right? The same thing is now applicable for the hidden layer also. The output from the hidden layer, for example, the output from the first neuron of the hidden layer will go as an input for all the neurons of the output layer. So the output from the output of the first neuron of the hidden layer will go as an input for all the neurons of the output layer. It goes as the input for the first neuron of the output layer, second neuron, third neuron, so on and so forth up to the nth neuron. Similarly, the output from the second neuron of the hidden layer also goes as an input to the first neuron, second neuron, and nth neuron of the output layer, so on and so forth, right? And finally, the output from the output layers are the outputs. These are the actual outputs, okay? And now here also we'll have weights. Here also we'll have weights. So now how the weight matrix, now we'll have three weight matrix, because there will be a weight matrix. See, now we'll have three weight matrix. There will be a weight matrix associated with the input and the input layer. Okay, this is the actual input and this is the input layer, and we'll call this as weight matrix as W1, right? And there will be a weight matrix associated with the input layer and the hidden layer. We'll call it as W2, and there will be a weight matrix associated with the hidden layer and the output layer. That will be W3. Okay, so if you see this weights, so this will be what? This will be W11, okay, W12, so on and so forth, W1I, because there are I neurons, right? So from the second one it will be W21, W22, so on and so forth, W2I. Okay, so if you see, so the last neuron is WP1, WP2, W, so on and so forth, WPI, right? So what is the size of this weight matrix? It has P rows and I columns. So the weight matrix 1, it will have P rows and I columns. Similarly, if you do this weight matrix 2, so this will be, so this is what? So here the input layer contains I neurons and the hidden layer contains M neurons. The input layer contains I neurons and the hidden layer contains M neurons, right? So this weights, if you see, okay, so the output of this, I mean the size of this weight matrix will be I into M. It has I rows and it will have M columns, right? Okay. See, here we are, see, let us not, this weights, we have to use some other variable. Here we are using W11. So here also we cannot use W11. Here we can call it as V11. This is V11. From this to this, the weight is V11. This we can call it as V12. This we can call it as V1M. This we can call it as V21, V22, V2M. This weight we can call it as VI1, VI2, VIM. Okay. Similarly, if you see the weight matrix of this, the W3 weight matrix, it will be of size M into N. Again, here we have to use some other variable. As here we are using W, here V, here we can use, say we can use U. Okay. So this will be U11, U12, and this is U1N. This will be U21, U22, U2N, right? This will be UM1, UM2, so on and so forth, UMN, right? So this is how basically we define the weight matrices, right? Okay. So here we are not discussing like how we are going to adjust the weight matrix, all those things. So basically that will come in feedback neural networks. We are not getting into feedback neural network. We are just trying to understand the different types of neural networks. So this is the case with multi-layer feed-forward neural network. So in the last layer only we have the outputs. Okay. So this is the same diagram, nothing difference. So whatever we have discussed, that's what explained here. So there are basically three weights. So there is a weight, so W1, W2, and W3. So there is a weight between the input and the first layer, and there is a weight associated between first and the hidden layer, and there is a weight associated between the hidden layer and the lost layer. Okay. The output of the ith, jth, and kth neuron in any Lth layer is represented something like this: XI plus theta I. Right? So basically it's the same equation. There is no much difference, right? Okay. Next, let us talk about recurrent neural network. So far, whatever the neural networks we have discussed, there is no branches in that. So in recurrent neural network, we have feedback loops. So far, whatever we have discussed in those networks, there were no feedback. Whereas in recurrent neural network, there will be feedback. Right? The networks differ from feedback network architectures in the sense that there is at least one feedback. So in recurrent neural network, there will be at least one feedback. Okay. So there could exist one layer with feedback connection. There could also be neurons with self-feedback links. Okay, there can be also self-feedback links. That is, the output of a neuron is fed back into itself as input. So such neural network is called as recurrent neural network. So here is a typical architecture of a recurrent neural network is shown. Here you can see the output of this neuron is given as a input to the first neuron, and here we have a self input. The output of the neuron itself is given as its own input. Here the output of this neuron goes back to one layer, and it comes as an input to the one of the neurons, right? So depending on the type of the feedback loops, this recurrent neural network, we have several types of recurrent neural network differing depending on the type of the feedback loops. So like they are called with various names like Hopfield network, Boltzmann machine, so on and so forth. Right? Okay. So now you may be asking, you may be wondering like why we have different types of neural network. Why can't there be one neural network? The reason is depending on the type of the problem we are going to address, we have to use the appropriate type of the neural network. So there is no universal formula to use only one neural network. With one neural network, we cannot provide solution for all the problems. So depending on the type of the problem, we have to choose the appropriate neural network. So that's the point here. Okay. So here we have a neural network. This is basically a neural network to solve a linear equation. Say there are two inputs x1 and x2. Some weight is associated w1, w2. So this x1 goes as an input, right? And also we are considering some theta. This is considered as bias. So basically, this neural network represents this equation. Here, this is input. This is not a layer. This is input. We have only one layer. This is the layer. This is the neuron, right? This is input. Or this, instead of writing the theta here, so this is little misleading from the previous understanding. Instead of writing the theta here, you can write the theta here. Okay. Instead of writing x1 here, you can write here. X2 you can write here. So these are inputs. So this neural network is represented through this function. F is equal to W0 into theta. This is a bias term, W0 into theta, plus W1 x1 plus W2 x2, right? So basically this is a bias term. So we are representing as B0 plus W1 x1 plus W2 x2. So this represents basically a linear equation. Okay. Now, if you see, some of the problems are linearly separable, whereas some of the problems are not linearly separable. Say this is an example of a type of a problem which is linearly separable. That is, with a straight line, you can separate the problem into two classes. Whichever the solutions which is coming to the right side of the line, they fall under one class. And the solution which comes under the left side of the line, they fall under a different class, right? So this is the case for, so this is typically an example for the problems which are linearly separable, whereas this represents the problem which is not linearly separable. Now this problem, you cannot separate it linearly. There is no straight line which can separate it, because if you see, some part of the problem is like this, so you cannot use a straight line to separate this. So now, if a problem is linearly separable, okay, if a problem is linearly separable, then it can be solved by using single layer feed forward neural network, right? But if a problem is not linearly separable, then to solve it, we need a multi-layer feed forward neural network. Okay, so that's the point. So let us consider an example for a linearly separable problem and a linearly non-separable problem. So again, let us revisit the logic gates. So let us consider the AND logic So this is AND logic, which I already discussed. This is XOR logic. We have two inputs and one output, X1, X2, and output Y. So you know the working of the XOR logic. When the inputs are different, the output will be 1. When the inputs are same, the output will be 0. So when the inputs are 0, 0, the output is 0. When the inputs are 1, 1, also the output is 0. When the input is 0, 1, the output is 1. And the input is 1, 0, also the output is 1. Okay. So this is about the XOR truth table. Now, if we plot this, as a graph by keeping x1 and x2, right? By considering one axis as x1 and another axis as x2, okay? And if you plot, what you will get? Say this is 0, 0, okay? So this point is x1, 1. This point is x2 is 1, right? So if you plot for AND, 0, 0, when x1 is 0 and x2 is 0, the output is 0. So you got here, okay? When x1 is 0, and x2 is 1, when x1 is 0 and x2 is 1, then also it is, the output is 0 only, okay? Right? It is okay. So it is not just the output. Let us recall that previous equation. What is the previous equation we formed for the AND gate? The AND gate equation is this. This is the equation: 0.5 x1 plus 0.5 x2 minus 0.9. 0.9 is the threshold, so it should be basically subtracted, right? So 0.5 x1 plus 0.5 x2 minus 0.9. So when x1 is 0 and x2 is 0, if you apply in this equation, what you will get? It is 0.5 x1, that is 0 into 0.5 plus 0 into 0.5, that is 0. 0 minus 0.9 is 0 minus 0.9. It is minus 0.9, right? So when x1 is 0 and x2 is 0, you are getting an output of minus 0.9, okay? And whenever the output is less than the threshold, what is the final output? Final output is 0, okay? So we got this point, right? This is one case, okay? Next, second case is when x1 is 0 and x2 is 1. When x1 is 0, it is 0 into x1, 0 plus 1 into 0.5, 0.5 minus 0.9 is 0.5 minus 0.9 is, again it is minus 0.4. Again it is less than 0. Again it is less than 0, right? So here also our score is here only, right? For 1, 0 also it will be here only, right? For 1, 1, when it is 1, 1, it is 1 into 0.5 plus 1 into 0.5, right? 1 into 0.5. So it is 0.5 plus 0.5, which is 1 minus 0.9. 1 minus 0.9 is 0.1. 1 minus 0.9 is 0.1. Okay. Okay. See, basically it shows that when the input, when x1 is 0 and x2 is 0, the output is 0. That represents this point. So this is what, this is for x1 0 and x2 0, the output is 0. Okay. When x1 is 0, okay, and x2 is 1. X1 is this line, right? X2 is 1. Then also the output is 0, right? So for this point also the output y is 0. For this point also the output y is 0. Okay. The third point is x1 1, x2 0. So x1 1, x2 is 0. For this point also the output is 0. The last point is x1 1, x2 1. So x1 is also 1, x2 is also 1, right? For this point, x1 1 and x2 1, for this point the output is 1. Okay. For all the remaining points the output is 0. For the last point alone the output is 1. Now this is basically it is a linearly separable problem. Okay, it is a linearly separable problem. With a straight line we can separate it, right? So here this is 0 0, this is 0 0, this is 1 0, this is 0 1. Okay, in all these cases the output is 0. Only for 1 1 case the output is 1. So with a straight line we can separate it. As this is a linearly separable problem, this can be represented by using a single layer feed forward neural network. And that's what the example we have discussed the neural network, right? But if you consider the XOR case, see, this is the truth table corresponding to XOR. So see, XOR, if you see 0 0 output is 0. So this point is 0 0, output is 0. 0 1, x1 is 0 and x2 is 1. This point is 0 1. When the right, so this point is 0 1. For 0 1 output is 1. Okay, for 1 0, so this is 1 0. For 1 0 also output is 1. For 1 1 the output is 0. Now this is not linearly separable. You cannot draw a straight line and you cannot separate zeros and ones. So here also you have zeros. You cannot draw any type of straight line to separate the zeros from ones. So this is basically a linearly non-separable problem. Okay, because all ones are at some place and all zeros are at some other place. So if you see here, this is 1 and you have to something like this. So this is not a linearly separable problem. In such case, what we need is a multi-layer feed-forward neural network. Okay. Now let us. So we need more than one layer, right? So this is the crux. Any linearly separable problem can be solved with a single layer feed-forward neural network. For example, AND problem, it's a linearly separable problem. On the other hand, if the problem is non-linearly separable, then a single layer neural network cannot solve such a problem. To solve such a problem, we need a multi-layer feed-forward neural network. Okay. Now this is one example. Here all the weights were given, but this is an example of a multi-layer feed-forward neural network for solving the XOR problem. Here we have two layers, right? Here we have two layers. This is one layer, okay, and this is another layer. So there is no hidden layer. This is the input layer, and this is the output layer. These are actual inputs. This is not a layer. X1 comes here, X2 comes here. These are the weights, right? The weight from X1 to the first input to the first neuron is 1. First input to the second neuron is also 1. Second input to the first neuron, the weight is 1. Second input to the second neuron also the weight is 1. And the weight from the first neuron of the input layer to the output layer is 1. And the weight from the second neuron of the input layer to the output layer is -1. Okay. So this is how it is defined. Now let us see, like, let us try to plug some values and let us see how it works. Say if the input is 0, both are zeros, then what happens? This is 0 into 1. So here what you get is 0 into 1. This is threshold. 0.5 is threshold for this neuron and 1.5 is threshold for this neuron. Okay, right? And another important thing, if this value is greater than 0.5, it is going to produce 1. This neuron, whereas if it is greater than 1.5, it is going to produce -1. Okay, so it is not always that if it is greater than the threshold, it should produce 1. So it depends. This neuron, if it is greater than, if this input is greater than 0.5, it is going to produce 1. Otherwise, it produces 0. Whereas this, if it is greater than 1.5, it produces -1. Otherwise, it produces 0. Okay. So this is what 0 into 1 plus 0 into 1, which is 0. Is 0 greater than 0.5? No. So it produces 0. Okay. Similarly, see this case also. Similarly, if you see this case, here also the same case, it is 0 into 1 plus 0 into 1, which is 0. Is 0 greater than 1.5? No. So it produces 0. So 0 into 1 is, this is 0 into 1 is 0. 0 into -1 is also 0. So 0 plus 0, 0. Is 0 greater than 0.5? No. So the output is 0. This is the case for both inputs are 0. Now if both inputs are 1, then let us see what happens. If both inputs are 1, if this is 1 and this is 1, then here what you will get, 1 into 1, this weight 1 into 1 plus 1 into 1, which is nothing but 2. Is 2 greater than 0.5? Yes, 2 is greater than 0.5. So the output is 1. Here, this is weight. This weight you should multiply. So 1 into 1 is 1. Again here, this is 1 into 1 plus 1 into 1, which is 2. Is 2 greater than 1.5? Yes, 2 greater than 1.5. So what is the output it produces? So the output it produces is, sorry. See, this is threshold. This is threshold, right? So this is 1 into 1 plus 1 into 1. So the output is 2. Is 2 greater than 1.5? Yes, 2 greater than 1.5. So this is the output produced is minus 1. I'm sorry, this is not the weight. You need not multiply anything here. Previously I said this is weight. It's not weight. So it is 1 into 1 plus 1 into 1 is 2. Is 2 greater than 0.5? Yes. So the output is 1. That's all. Okay. Here the output is minus 1. Now both were added here just. 1 minus 1 is what? 1 minus 1 is again 0. So when the input, both the inputs are 1 also, the output is 0. Right? Let us take the case for 0, 1. Let us take the case for 0, 1. If the input is, if one input is 0, the other input is 1. So here what happens? 0 into 1 plus 1 into 1, which is nothing but 1. Is 1 greater than 0.5? Yes. So this output is 1. Here also, here it is 1 into 1 plus 0 into 1. The output is 1. Is 1 greater than 1.5? No. So the output is what? 0. Okay, if it is greater than 1.5, it will be minus 1, otherwise it will be 0. So 1 plus 0 is what? Here it is just added. 1 plus 0 is what? 1. So the output is 1, right? Similarly, the other case is 1, 0. The other case is 1, 0. So if you consider the case of 1, 0, this is 1, 0. So it is 1 into 1 plus 0 into 1. 1 into 1 plus 0 into 1, which is 1. Is 1 greater than 0.5? Yes. So the output is 1, right? Similarly, this case, if you take, it is 0 into 1, 0 into 1 plus 1 into 1, which is 1. Okay, is 1 greater than 0.5? 1.5? No. So this is 0, this is 1. So 0 plus 1 is again 1, right? So basically, like that, it works for all the cases, right? 0, 0 case also we can see once again, because this is not weight, this is output, right? So it is 0 into 1 plus 0 into 1, which is 0. Is 0 greater than 0.5? No. So this is 0. 0 into 1 plus 0 into 1, it is 0. Is 0 greater than 1.5? No. So this is 0. So 0 plus 0 is 0, right? Is now this will be trigger only if it is greater than 0.5. 0 plus 0 is 0. Is 0 greater than 0.5? No. So the output will be 0. In other cases, this is 1. So is 1 greater than 0.5? Yes. So the output becomes 1, right? So that is how this what you call the XOR gate works. So to represent an XOR, we need a multi-layer feed-forward neural network, right? Okay. So the next type of neural network is dynamic neural network. So in some cases, so in dynamic neural network, basically we will be comparing the output. So whatever the output we are getting, that is called as the actual output. The output will be compared with the target, that is the expected output, and based on the error, the weights will be adjusted. Okay. So whatever we have discussed so far, they are static neural network, because here we are fixing the weights. We are not learning the weights. With the understanding of the problem, we are fixing the weights, and with the input, it is working. This is just for understanding, but in real life, we don't use neural networks for this type of problem. We initially assign some random weights, and then we produce some output. So that output is called as the actual output. Then during the training phase, the actual output will be compared with the expected output. Then the error will be created, and we'll take the square of the error. Based on this error, the feedback will be given, and accordingly the weights will be adjusted. So that technique is called as back propagation. And back propagation, basically it is used in a dynamic neural network, and the architecture is shown here. The inputs go to the neural network architecture, output Based on the output, we calculate the error. So how we calculate the error is this is actual output minus target. Target means what is the expected output. Both we will subtract, and based on that, we'll give a feedback to the neural network. And based on this feedback, the weights will get adjusted. So the entire thing what we are doing is we are only adjusting the weights. So the whole process, what is happening in the neural network is to identify the proper weights so that the input can be mapped with the output. So when you do that with different samples of data items, finally the weights will be fine tuned, and it will be fine tuned such a extent that it will be able to map any input to the respective output. Okay. So the conclusion is what we have discussed in this session is for a linearly separable problem, we can use single layer feed forward neural network. For a non-linearly separable problem, we should use multi-layer feed forward neural network. For problems with for real-time problems like face recognition or object detection, all such problems, you cannot use static neural network. We need dynamic neural networks. In dynamic neural networks, during training phase, we calculate error. Error is calculated by comparing the actual output with the expected output or the target output. And based on that, the feedback will be given to the neural network, and accordingly, its weight will get adjusted. Okay, fine. Thank you. So let us stop here for today's session.